Tonight, we're going to explore one of the most counterintuitive arguments in the future of human spaceflight. For decades, the logic has felt obvious. The moon comes first. It is 3 days away. 6 crews have already walked its surface, and Mars sits 6 long months across deep space. Closer has always meant easier. Proximity has always felt like destiny. But that instinct may have it exactly backwards. Because when you stop measuring distance and start measuring what actually keeps a human alive, radiation, temperature, dust, water, gravity, the entire picture flips. The moon, the closer world, turns out to be the deadlier one. Its surface absorbs 4 times the yearly radiation a nuclear worker on Earth is ever allowed. A solar flare gives you 30 minutes of warning, and walls a fraction of an inch thick to hide behind. Mars, hundreds of times farther away, is the gentler world. The closer world is the one trying to kill you. So why have we been planning it the wrong way around? And what happens to the dream of leaving Earth once you realize the easy first step was never easy at all? By the end of tonight, you're going to understand why radiation, temperature, dust, and gravity all quietly favor Mars, how the moon hides its hostility behind the comfort of being close, and what this single inversion means for the real timeline of becoming a species that lives on more than one world. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. The year 1969 settled something. Neil Armstrong stepped onto the lunar surface, worked, and came home alive. The Apollo program did it 6 times. Whatever else was uncertain about space exploration, that one fact was not. Humans could land on the moon, and so the logic that followed felt almost inevitable. You already know the moon works. It is 3 days away. Mars is 6 months away and has never been visited by a human being, only by robots crawling slowly across its rust-colored plains. Build a base on the moon first. Learn to live off Earth. Fix the problems in a place where rescue is 3 days away rather than 6 months. Then apply those lessons to Mars. The moon as a stepping stone. The moon as the obvious first choice. It is a reasonable argument, and for decades it has shaped how engineers, mission planners, and space agencies think about the future of human expansion. But here is where it gets strange. When you measure the two worlds against the factors that actually decide whether a human being can survive there for years, not days, the picture does not simply adjust at the edges. It inverts. Proximity turns out to matter far less than environment, and the environment of the moon, on almost every count, is more hostile to long-term human survival than the environment of Mars. The first place you see this is radiation. Start with where you are standing right now. Earth is surrounded by a magnetosphere, a vast invisible shield generated by the planet's molten iron core. It extends thousands of miles into space in every direction. It deflects most of the charged particles constantly streaming outward from the sun, the solar wind, and absorbs or redirects the high-energy cosmic rays that arrive from deeper in the galaxy, from supernovae and the neighborhoods of black holes. Everything living inside that shield barely registers the radiation that exists outside it. The magnetosphere is not a convenience. It is the reason complex life exists on this planet at all. The moon sits at 238,000 miles from Earth. At that distance, it passes through the trailing extension of Earth's magnetosphere, called the magnetotail, for only a few days each month. The rest of the time it is fully exposed. No magnetic field of its own. No atmosphere to speak of. The solar wind reaches the surface directly. Cosmic rays slam into the regolith, the loose rocky powder that covers the moon, without losing meaningful energy on the way down. The moon is, for most of each month, unshielded in a way that the surface of Earth never is. Now add solar flares. The sun periodically erupts. The most powerful category, called X-class flares, releases enormous bursts of radiation and accelerates charged particles to near relativistic speeds. The first things to arrive after a flare are light, X-rays, and extreme ultraviolet radiation. They travel at the speed of light, arriving 8 minutes after the flare erupts. Those are dangerous, but survivable with minimal shielding. The problem is what comes next. The real threat is the solar energetic particles, protons and heavy ions, moving fast enough to penetrate most materials. They arrive somewhere between 10 minutes and several hours after the flare, depending on the path they travel through space. Once they arrive, bombardment can last hours, sometimes days. This gives a crew working on the lunar surface a practical warning window of roughly 30 minutes to an hour before the main particle storm arrives. In some cases, less. Here is what one sievert does to a human body. It causes radiation sickness, nausea, fatigue, immune suppression. 5 sieverts kills roughly half the people exposed within a month. 10 sieverts kills everyone. A major solar storm on the lunar surface with no shielding can deliver several sieverts in a single day. Not a long-term hazard. Not something that accumulates over years. Several sieverts. One day. So the habitat must provide shielding. And this is where the engineering becomes unforgiving. A typical aluminum wall a few tenths of an inch thick, the kind used in spacecraft, stops low-energy particles reasonably well and is nearly transparent to the high-energy ones. It offers almost no protection against the radiation that actually kills. Real protection requires several feet of rock or regolith piled on top of and around the habitat, at minimum 6 feet. For the worst storms, 10 feet or more. That means underground or heavily buried. And it means not just the habitat. It means every location where crew members work on the surface. Think about the operational reality. A crew is conducting a geology survey 2 miles from the main habitat. A flare erupts. 30 minutes until the particle storm arrives. A rover on the lunar surface does not move quickly, and soft terrain slows it further. Driving 2 miles back to base is not possible in 30 minutes under realistic conditions. This forces a different design entirely. Emergency radiation shelters must be distributed across the operational area, close enough to reach on foot or by short rover drive, roughly every 3 miles. Each of those shelters needs its own life support system, its own power source, its own communications, and its own excavated and reinforced structure. This infrastructure does not reduce the radiation problem. It manages it, and it must be built before any surface work begins. But the solar flares are not the slow killer. They are the dramatic one. The slow killer is the background. Even between flares, even during quiet periods when the sun is calm, the lunar surface receives continuous radiation. The background dose runs about 0.2 millisieverts per day. That works out to roughly 200 millisieverts per year. The occupational limit for radiation workers on Earth, people who work in nuclear power plants or hospitals using radiological equipment, is 50 millisieverts per year. The lunar background, on an average day with no solar activity, is 4 times that limit. Every year. Continuously. Spend 10 years on the moon, in background conditions only, before any solar storms are included, and you accumulate approximately 2,000 millisieverts of radiation exposure. That is a measurable increase in cancer risk. Spend 20 years, and the probability becomes significant. This is not science fiction speculation. This is the straight arithmetic of dose. And now Mars. Mars has no global magnetic field. Its core cooled billions of years ago, the internal dynamo shut down, and whatever magnetosphere it once had dispersed. On paper, this sounds exactly as bad as the moon. No magnetic protection, exposed to the same solar wind and the same cosmic rays. Wait, that is not quite right. Mars has an atmosphere. Thin, far thinner than Earth's, less than 1% of Earth's atmospheric density. It does not retain much heat. It cannot support unprotected breathing, but it is there. And even that thin layer of carbon dioxide acts as a radiation shield. Scientists describe its protective value as roughly equivalent to 6 inches of water. That is enough to block a substantial fraction of incoming radiation. The solar wind, mostly stopped. Lower energy cosmic rays, significantly reduced. High energy particles, meaningfully attenuated. The result is that the surface of Mars receives about 0.2 millisieverts per day at solar minimum, close to the same as the moon. But then comes a counterintuitive reveal. At solar maximum, when the sun is most active, The dose on the Martian surface drops to about 0.15 millisieverts per day. Not increases, drops. The reason is that enhanced solar magnetic activity sweeps outward through the solar system and deflects many of the extrasolar cosmic rays before they reach Mars. More solar activity, fewer deep space particles arriving at the surface. The annual dose on Mars runs between 60 and 70 millisieverts, higher than Earth, but comparable to what many radiation workers on Earth are already permitted to receive, manageable with basic precautions. And Mars has something else. Billions of years ago, ancient volcanoes built lava tubes across the Martian surface, channels where flowing lava carved out enormous hollow passages beneath the ground. Many of them collapsed long ago, but thousands survived intact, roofed over by the same rock that formed them, some hundreds of feet wide, some stretching for miles. Inside a sealed and pressurized lava tube on Mars, the radiation environment drops to near-Earth levels. The roof above provides the mass that blocks high-energy particles. No excavation needed. No constructed shelter. The geology already built it. The Moon has lava tubes too, but location makes them nearly useless. Most sit near the equator, where daytime surface temperatures reach 260 degrees Fahrenheit. The polar tubes, where temperatures are more stable, tend to be small, structurally compromised, or difficult to access. And any lava tube on the Moon still requires the same excavation, sealing, and pressurization as a purpose-built underground habitat. The natural advantage largely disappears. This is the first inversion. The world without a magnetic field turns out to have a better answer to radiation than the world that most people assumed was the safer starting point. The Moon's radiation problem is continuous, structural, and expensive to manage at every location where humans work. Mars's radiation problem, addressed with existing lava tube geology and the natural shielding of even its thin atmosphere, is manageable. Radiation was the first factor. It would not be the last. That 260 degrees Fahrenheit number is worth staying with for a moment. The Moon's surface at the equator reaches 260 degrees Fahrenheit during the day. That is hotter than the boiling point of water. Hot enough to cook food, hot enough to sterilize equipment. And then, when the sun drops below the horizon, the temperature does not gradually fall the way it does on Earth. It plunges. The surface drops to negative 290 degrees Fahrenheit at night. That is cold enough to freeze carbon dioxide out of the air, if there were any air to freeze it from. The swing between those two numbers is 550 degrees Fahrenheit. To put that in scale, think about the highest performance industrial ovens used in materials processing. Many of them operate across temperature ranges of a few hundred degrees. Engineers spend years designing materials that can survive those conditions. The Moon cycles through a range that large twice a month, every month, continuously, with no machinery involved and no way to prevent it. No other place humans might realistically visit behaves this way. Mercury is closer to the Sun, which should make it worse, but Mercury rotates so slowly and its surface is so dark that it actually accumulates less total swing than the Moon. The Moon's combination of no atmosphere, no moisture, no thermal mass in the regolith, and a fairly rapid day-night cycle relative to Mercury produces the most extreme surface temperature variation in the inner solar system. The engineering consequences are immediate. Metals expand when heated and contract when cooled. Across 550 degrees, that is not a minor effect. Seals crack, joints fail. Structural members warp out of tolerance. Every structure on the lunar surface needs expansion joints designed into it. The same way long bridges on Earth have small gaps built in to allow the steel to move. But on a bridge, the swing is maybe 100 degrees over a full year. On the Moon, the swing is 550 degrees over 29.5 days. Active thermal management consumes enormous energy. During the day, you are fighting to keep heat out, running cooling systems against a surface that wants to bake everything it touches. At night, you are fighting to keep heat in, running heaters against a surface that drops to temperatures deep enough to freeze electronic components solid. Neither phase is passive. Neither phase is cheap. But something was wrong. The real thermal problem on the Moon is not the temperature itself. Most engineers, when they first look at this problem, assume the solution is insulation. Build a good enough shell and you can keep the interior comfortable regardless of what the outside is doing. That logic works on Earth. It even works on Mars. On the Moon, it runs into something that insulation cannot solve. The lunar day is 29.5 Earth days long. That means 2 weeks of continuous daylight, then 2 weeks of continuous darkness. Not 2 weeks of warm days and cold nights. 2 weeks of unbroken sun, followed by 2 weeks of no sun at all. Think about what the 2-week daylight phase means for a base. The sun does not set. Temperatures climb steadily hour after hour, day after day, with no overnight cool down to reset the thermal load. By the end of the second week, the habitat and everything around it is heat-soaked. The regolith, the surface hardware, the thermal radiators, all of it has absorbed 2 weeks of direct solar energy with no relief. Managing that without burning through enormous power reserves requires engineering solutions that do not yet exist at any useful scale. And then the sun sets. The 2-week lunar night is a different kind of problem, and in some ways a worse one. No solar power. For 14 days, any base that depends on solar panels produces nothing. A solar panel sitting under a lunar sky at night is inert. The base runs entirely on what it stored, or on nuclear reactors. If batteries the mass required is staggering. Keeping life support, heating, lighting, and communications running for 2 weeks demands hundreds of tons of batteries, not hundreds of kilograms, hundreds of tons. A fleet of fully loaded semi-trucks weighs less. During that same 2-week darkness, the temperature outside drops continuously. Water in any unheated pipe freezes solid. Freeze-thaw cycles, even partial ones, destroy plumbing. Electronics begin to fail below certain temperatures, and battery chemistry itself degrades in the cold, meaning the very batteries you are depending on to survive the night are losing capacity precisely when the cold is worst. The alternative is nuclear reactors. Reactors work in the dark. They generate heat and power regardless of the sun. But reactors bring their own problems. Heat rejection requires radiator systems that must operate at the same extreme temperatures that make the moon difficult in the first place. Reactors require shielding to protect the crew from their own radiation output. They require fuel, maintenance, and redundancy. A nuclear lunar base is possible in principle, but it is not a simple engineering problem layered on top of an otherwise manageable situation. It is a second major infrastructure challenge added on top of the thermal one. Mars does not have any of this. The Martian day is 24 hours and 37 minutes long, barely longer than Earth's. Crews living on Mars fall into a sleep schedule almost identical to the one their bodies already know. Solar panels recharge every single day. Batteries need to cover roughly 12 to 14 hours of overnight operation. The same design window used in Earth-based solar installations on rooftops and in the desert. The engineering is understood. The supply chains exist. The math is familiar. Mars temperature swings are real. At the equator in summer, daytime highs can reach 70 degrees Fahrenheit. Nights drop to negative 100 degrees Fahrenheit. That is a swing of about 170 degrees. Significant, but within the range that conventional insulation, heat pumps, and standard materials can manage. The thin Martian atmosphere, less than 1% of Earth's pressure, still holds enough gas to moderate the transitions. Temperature does not crash instantly at sunset the way it does on the moon. It falls gradually. It rises gradually. The ground radiates slowly. The engineering response can be proportional. And for habitats built inside Martian lava tubes, the problem simplifies further. The temperature inside a sealed lava tube on Mars holds at roughly negative 60 degrees Fahrenheit year-round. Not warm, but constant. Constant is the key property. A habitat that faces a constant negative 60 degrees needs insulation and heating size for one condition, not a 170 degree swing between opposite extremes. Insulate the walls, run a heat source inside, and the interior reaches shirt-sleeve comfort with a fraction of the energy that lunar thermal management demands. The moon's temperature problem looks, at first, like a building science problem. It looks like insulation and thermal coatings and engineering discipline. That framing is not wrong, exactly. It just misses the 2-week cycle that turns a manageable engineering problem into an energy storage crisis. No amount of insulation eliminates the need for 2 weeks of stored power. No passive solution survives 14 days of accumulated solar heat, followed by 14 days of complete darkness. Mars, by contrast, solved the power problem simply by rotating the way Earth does. Temperature was the second factor. The next factor would take both of these and make them harder to fix. Now consider something less dramatic than radiation, less visible than temperature extremes, less urgent sounding than a 2-week blackout. Lunar dust does not announce itself. It does not arrive as a storm or a surge. It simply accumulates. And after decades of study, no one has found a reliable way to stop it. That is the genuine engineering assessment, not a dramatic one. Lunar dust is one of the most hostile materials in the solar system. Not because it is rare or exotic, because of what it is made of and how it behaves. To understand why, start with how it forms. Micrometeorites strike the lunar surface constantly. They arrive at velocities between 7 and 45 miles per second. In feet per second, that is somewhere between 23,000 and 148,000. A rifle bullet travels roughly 3,000 feet per second. These impacts arrive at 10 to 70 times that speed. At those velocities, both the incoming fragment and the surface material it strikes vaporize instantly into superheated plasma. The collision does not leave a simple crater. It leaves a cloud of ionized gas that cools and condenses back into solid particles. Particles shaped by that violent process. Particles shaped by nothing else. The moon accumulates roughly 100 tons of meteoritic material per day, spread across a surface of about 14 million square miles. Over 4 billion years, this process has ground the outer layer of the moon into a powder called regolith. That powder is typically several feet deep. In ancient regions, it can reach tens of feet deep. When the Apollo astronauts walked on the surface, their boots sank several inches into it wherever they stepped. Now here is where the chemistry becomes the problem. On Earth, sand and rock particles get tumbled by wind and water for thousands of years. The sharp edges wear away. The surfaces oxidize. The particles round off and coat themselves in stable mineral layers. The result is relatively inert, relatively safe. Beach sand is smooth enough to touch with bare hands. Lunar dust has never been tumbled. There is no wind. There is no water. There is nothing to round the edges or stabilize the surfaces. Under a microscope, lunar dust looks like broken glass. Jagged edges, sharp points, fractured crystal facets, tiny hollow spheres formed from impact-melted droplets, irregular shapes at every scale, all of it abrasive, all of it cutting at whatever it contacts. Think of microscopic sandpaper that never wears smooth. But the shape is only part of the problem. The chemical reactivity is the other part. On Earth, the moment a fresh rock surface is exposed to air, it begins to react with oxygen and moisture. An oxide layer forms within seconds. That layer is chemically stable. It insulates the surface from further reaction. Lunar dust has no such layer. The fracturing happens in a near-perfect vacuum, so the freshly broken surfaces are exposed directly to whatever they contact. The surface atoms are incomplete. They carry what chemists call dangling bonds, unsatisfied connections reaching outward, actively seeking something to bind to. When lunar dust contacts a suit material, a seal surface, a lens, a bearing, it does not just sit there. It tries to react. It bonds. Electrostatically, it clings. Chemically, it holds. Brushing it off removes some of it. Vacuuming removes more. Neither removes all of it. The dust that remains bonds harder with each contact, each pressure, each EVA. The Apollo missions found this out in detail. From Apollo 11 through Apollo 17, every surface mission encountered serious dust problems within days. Dust abraded the rubber O-rings inside suit joints, leaving fine scratches and creating slow leaks. Dust worked into bearings, grinding them stiff. Suit joints that required moderate force to flex after one EVA required noticeably more force after 3. After just 3 EVAs over 3 days, the suits had measurably degraded. Cameras developed permanently contaminated lenses. air filters loaded with fine particles and lost efficiency. Dust settled into electronics, into control panels, into equipment racks in the low gravity of the lunar module, floating across surfaces and settling into every gap. Harrison Schmitt, the geologist on Apollo 17, had an allergic reaction. Dust got inside the lunar module. He developed an inflamed nose, watering eyes, difficulty breathing. His symptoms eased after a few hours as his body adapted to the exposure. But those were 3 days of exposure at most. Apollo's longest lunar surface stay was 3 days. Now think about what happens to a permanent base. Every EVA brings dust back inside. Every airlock entry, every suit removal, every equipment transfer. Over weeks, the contamination spreads. Over months, it saturates the habitat. The fine particles are sharp enough to penetrate deep into lung tissue. The chemical reactivity may trigger immune responses, the way freshly fractured silica does in coal miners. The condition called silicosis, a progressive scarring of lung tissue that has no cure and worsens with continued exposure. Apollo astronauts were not exposed long enough to develop it. A crew living on the moon for years would face a fundamentally different risk profile. We do not fully know what that profile looks like, because no one has ever been exposed long enough to find out. NASA has researched this problem for decades. The proposed mitigations are extensive. Multi-stage airlocks with dust removal between chambers, thorough suit vacuuming before entry, electrostatic removal systems that use charge to lift particles from surfaces, special coatings designed to reduce adhesion, brushes and wipers at every entrance, isolated suit storage rooms that keep contaminated suits away from habitat air, routine cleaning estimated at 10 to 15 minutes per airlock entry, frequent filter replacement, dust-tolerant seal designs, bearings engineered to operate despite particulate contamination. Wait, none of them work reliably. Not partially effective, not almost effective. None of the proposed systems has demonstrated the ability to prevent lunar dust contamination in testing. Each approach reduces dust transmission by some amount. None reduces it to zero. And on a permanent base, 0 is the requirement. Not 90% removal, not 99%, because the dust that gets through today adds to yesterday's dust. The accumulation is continuous. The degradation is continuous. The base needs surfaces dust will not stick to. It needs cleaning methods that actually remove all of it. It needs seals that do not abrade and bearings that do not grind. None of those materials or methods currently exist in a form proven to work in lunar conditions. Apollo's solution was straightforward. Come home before the problems compound. 3 days is short enough that degraded suits, loaded filters, and contaminated equipment are manageable. The crew returns, the equipment gets examined, lessons are recorded for the next mission. A permanent base cannot do that. There is no coming home. The suits have to function indefinitely. The filters have to keep working. The seals and bearings and air systems have to hold. Radiation has a solution. Depth of rock or regolith stops it. Temperature has a solution. Stored energy and smart habitat design address it. Lunar dust does not yet have a solution. It is not a conventional engineering problem with a known answer waiting to be implemented. It is a fundamental materials and chemistry problem. It needs materials that do not yet exist, combined with cleaning methods that do not yet work, maintained against a contaminant that actively seeks to bond with whatever it touches. Less dramatic than a radiation storm, quieter than a 2-week blackout, but potentially the one problem that ends a permanent lunar base, not in a crisis but in a slow accumulation of failures. Suits that lose function, filters that clog, seals that leak. On the moon, equipment failures are not inconveniences. They are fatal. Dust was the third factor. And unlike the first two, it did not come with a clear path toward fixing it. On Mars, the same word means something very different. Dust on Mars is not the fractured, chemically hungry material that ended every Apollo mission early and threatens to end a permanent lunar base through slow accumulation of failure. It is something else entirely. Something that, by comparison, almost feels manageable. The reason comes down to one feature the moon does not have: an atmosphere. Mars has a thin one, thin almost beyond imagining. The surface pressure on Mars is about 600 pascals. Earth's surface pressure is about 100,000 pascals. That means the Martian atmosphere has less than 1% of the density of the air you are breathing right now. It is far too thin to breathe. It is far too thin to slow a landing spacecraft without help. But it is thick enough to move. It is thick enough to carry particles. And it has been doing exactly that for at least 3 billion years. Wind creates erosion. Erosion rounds particles. On the moon, a dust grain fractures and stays fractured forever, preserving every sharp edge in perfect vacuum with no force to wear it smooth. On Mars, a dust grain fractures and then the wind picks it up, carries it, tumbles it against other grains, and begins to round it. 3 billion years of that process produces something fundamentally different. Martian dust particles average about 3 micrometers in diameter, roughly 0.02 inches, finer than talcum powder. They float and suspend and coat every surface they contact. But they are not sharp. The edges are rounded. The chemical reactivity is low. They do not bond to surfaces the way lunar dust bonds. They settle. And crucially, they brush away. This difference changes almost everything about the dust problem on Mars. Almost everything. Because Mars dust comes with a problem the Moon does not have at all. Global dust storms. Every few Martian years, unpredictably, a regional storm begins somewhere on the surface. It kicks dust high into the thin atmosphere. The dust absorbs sunlight. The absorbed sunlight warms the air around the storm, creating winds. The winds kick up more dust. The system feeds itself. Within weeks, the storm can encircle the entire planet. In late May of 2018, that is exactly what happened. A regional storm in the northern hemisphere expanded. It spread. By June, it had grown into a planet-wide event. By its peak, the optical depth of the atmosphere exceeded 10. Optical depth is a measure of how much light is blocked. An optical depth of 10 means less than 1% of direct sunlight was reaching the surface. The sky turned orange-brown. Surface features became invisible from orbit. It lasted until September. Nearly 4 months of near-total solar blackout across an entire planet. For a solar-powered surface asset, this is not a challenge. It is a shutdown. Opportunity knew this firsthand. Opportunity had landed on Mars in January of 2004. Its planned mission was 90 days. It ran for 14 years. Engineers had watched the rover perform well beyond every expectation, powered by solar panels that the Martian wind cleaned regularly enough to keep the system alive. But in June 2018, the dust accumulated faster than any cleaning event could counter. The panels dimmed. The rover entered low-power mode, trying to conserve whatever charge remained. The storm did not break in time. The electronics cooled beyond recovery. In February of 2019, after more than 5,000 Martian days on the surface, NASA declared opportunity lost. A global dust storm blocking 99% of sunlight for months sounds like the most dangerous thing on the planet. It sounds like the single factor that ends all discussion of Mars as a place humans can survive. But the reality was different. It is not fatal, not unsurvivable, not even close to a deal breaker for a prepared base. The reason is threefold. First, these storms are predictable in their pattern. They happen every few Mars years, not every few months. A base plans around them. Second, they do not arrive without warning. They start regionally. Orbital observation gives weeks of advance notice before a regional storm becomes a global one. A prepared crew does not wake up one morning with the sky already dark. They watch the storm build from orbit and prepare. Third, and most importantly, a well-designed Mars base does not depend solely on solar power. Small fission reactors are currently in development for both lunar and Martian use. A Mars base would combine solar panels for normal operations with a nuclear backup that functions regardless of what the sky looks like. Darkness does not stop a reactor. Dust on a panel does not affect a fuel rod. Opportunity died because it only had solar panels and no way to heat itself through the dark. A crewed base would have neither of those limitations. And then, there is the cleaning. This is the part of the Martian dust story that no one expects. The same wind that picks up dust and spreads it across the planet also puts it back down. Martian dust settles under gravity. The smoother, less reactive particles do not grip surfaces the way lunar dust grips them. And periodically, dust devils and localized gusts sweep across the surface with enough force to lift the settled dust off whatever it has coated. Engineers on the Spirit and Opportunity missions watch this happen repeatedly. Solar panel output would slowly decline as dust accumulated. Then, sometimes overnight, it would jump back up. No command sent, no intervention. The wind had cleaned the panels. Without those cleaning events, Spirit and Opportunity would have been buried under accumulated dust within their first Martian year. With them, Spirit operated for more than 2,000 Martian days. Opportunity exceeded 5,000. The same wind that created the 2018 catastrophe was also the thing that kept both rovers alive for over a decade. The moon has no such mechanism. No wind, no cleaning events, no second chances. Once dust lands on a lunar panel, it stays there until a crew member in a spacesuit climbs out in full radiation exposure and removes it by hand. Every time. The material difference goes further. Martian dust is less abrasive to mechanical components. Rover wheels on Mars wear from sharp rocks underfoot, not from dust attacking seals and bearings from within. Curiosity has operated since August of 2012. Perseverance has operated since February of 2021. Wheels show damage, but arm joints still move. Camera lenses still image. Seals still hold. The mechanisms designed to last for years have lasted for years, some approaching or exceeding a decade and a half of continuous operation. The contrast with lunar hardware is not subtle. Apollo suits showed measurable degradation after 3 days. Curiosity has been functional for over 13 years. The material hostility of these two environments is not similar. It is not even close. Martian dust is a real problem. Global storms are serious. Panel coverage is real. The 2018 storm that ended Opportunity is a genuine warning about what solar dependency alone cannot survive. But predictability, orbital warning time, nuclear backup, and natural cleaning events together convert what looks like a planet-killing scenario into a manageable engineering challenge. The same challenge faced and solved for years at a time by machines never designed with permanent survival in mind. Dust was the fourth factor. And on Mars, for the first time in this comparison, the factor came with answers already demonstrated in the field. The next factor was not about the environment around a base, it was about the human body inside one. Of all the factors in this comparison, one stands apart from the rest. Not because it is the most dramatic on the surface, not because it generates the most striking numbers, but because everything else depends on it. Radiation shielding, temperature management, propellant production, food, air, the ability to return home at all. Every one of those problems is either solved or made unsolvable by a single question. Where is the water, and can you actually reach it? Both worlds have water. That matters. It took decades to confirm, and the confirmation came from multiple directions at once. India's Chandrayaan-1 spacecraft used infrared spectrometry to detect water molecules on the lunar surface. NASA's Lunar Reconnaissance Orbiter followed with radar mapping and neutron spectrometer data. Then, in 2009, NASA deliberately crashed a rocket stage into a permanently shadowed polar crater in an operation called L-Cross. The impact plume was analyzed in real time. Scientists found water. They also found carbon dioxide, methane, and ammonia. The moon has ice. Billions of kilograms of it, locked in its polar cold traps. That is the setup. Here is the reveal. Knowing the water is there is not the same as being able to use it. The ice is not sitting in sunlit fields, waiting to be scooped up. It is trapped inside permanently shadowed craters at the lunar poles, craters that have not seen direct sunlight in billions of years. The temperatures inside never rise above negative 250 degrees Fahrenheit. Some crater floors reach 25 Kelvin. That is negative 415 degrees Fahrenheit. Colder than Pluto's surface during its daytime. Colder than most locations anywhere in the outer solar system. There is no warmer part of the year. There is no morning when things thaw slightly. The shadow is permanent. The cold is absolute. The water accumulated the way many things do on the moon. Slowly, over geological time. Comet impacts delivered water molecules across billions of years. Solar wind protons reacted with oxygen in lunar minerals and produced additional water. Volatiles migrated across the surface and settled into the coldest available points, which are exactly those permanently shadowed floors. The physics is elegant. The consequence is brutal. Think about what entering one of those craters requires. There is no sunlight, so there are no solar panels. You must run power cables from the crater rim or deploy a nuclear reactor designed to function at 25 Kelvin. That reactor does not yet exist in deployable form. The engineering community is working toward it. It has not been built, tested, or flown. Every tool, every structural element, every piece of machinery inside the crater must be actively heated. At those temperatures, steel behaves like glass, rubber and plastics shatter, lubricants freeze solid, transistors fail below roughly negative 250 degrees Fahrenheit. Lithium-ion batteries stop functioning around negative 40 degrees Fahrenheit. You need thousands of watts of lighting just to see. You need heating on everything, continuously. The power demand to simply exist inside that crater before extracting a single gram of ice is enormous. But something else was happening. Even once you solve the power problem, the ice itself fights back. The water is not waiting in blocks. It is dispersed through the regolith, mixed into the soil at low concentrations. A reasonable working estimate is around 5% by weight. To extract 1 kilogram of water, you must process 20 kilograms of regolith. Every kilogram of water requires heating 20 kilograms of frozen rock dust from 25 Kelvin up to roughly 200 Kelvin, a temperature rise of about 175 degrees Fahrenheit, before the ice even begins to sublimate. Regolith has a specific heat of roughly 150 joules per gram. Water's latent heat of sublimation is approximately 2,800 joules per gram. Add those together across the concentrations involved, and you arrive at roughly 3 megajoules of energy per kilogram of water extracted. That is approximately the energy content of 1/10 of a kilogram of gasoline. Except, gasoline is not available on the moon. Every joule has to come from a reactor or a cable running down from the crater rim. After the ice sublimates, the vapor must be collected, condensed into cold traps, purified, because the ice contains other volatiles and fine dust. All of this happening in pitch darkness at negative 250 degrees Fahrenheit. And reactors compound the problem further. They generate waste heat that must be rejected through radiators. Radiators work by radiating heat to a cold environment. At extremely low ambient temperatures, the temperature differential is large, which sounds helpful, but the surrounding structures and equipment are also at those temperatures, which means thermal management becomes an exercise in managing heat flow in all directions simultaneously, with no margin for error. The result is this. Lunar water may be the single most expensive commodity ever acquired by human civilization. Not in some abstract sense. In the literal accounting of energy, equipment, engineering complexity, and human risk required to obtain 1 kilogram of usable water from a permanently shadowed polar crater at 25 Kelvin. This is the fifth factor. And unlike the first four, it does not compare two versions of a hard problem. It compares a solvable problem against one that may not be solvable at the scale a permanent base requires. The water question was always going to determine whether either world could sustain human life without a continuous supply chain from Earth. On the moon, the answer requires technology that does not yet exist, energy budgets that strain current engineering, and conditions that are more hostile than almost anywhere else in the solar system. What that answer looks like on Mars is the next part of this story. On Mars, the same question has a different answer, not a harder version of the same answer, a different one entirely. The North Polar Cap of Mars stretches roughly 600 miles across. It rises nearly 2 miles at its thickest point. The volume of water ice locked inside it is approximately 400,000 cubic miles. That is about half the volume of the Greenland ice sheet. And it sits on the surface, exposed to orbital cameras, reachable by spacecraft, accessible to anyone who lands nearby. During the Martian summer, the seasonal layer of carbon dioxide frost that blankets the pole each winter sublimates back into the atmosphere. That CO2 layer can be over 3 feet thick in winter. When summer arrives and polar temperatures climb to around -50 degrees Celsius, -58 degrees Fahrenheit, the dry ice goes first, and what remains underneath is essentially pure water ice. Minimal processing required, no extreme cold traps, no permanent darkness, no engineering systems that do not yet exist. But the poles are not even where the story gets most interesting. Mars Reconnaissance Orbiter has mapped enormous deposits of water ice sitting between 30 and 60 degrees latitude, north and south, not at the poles, at mid-latitudes, where future missions are more likely to land. In many of these regions, the ice begins just inches below the surface. A few inches of dry Martian soil, and then pure ice underneath, the frozen remnant of an earlier era when Mars tilted differently on its axis, and ice could accumulate at lower latitudes. These are essentially underground glaciers, buried shallow, waiting. Erosion has exposed some of them directly. Orbital imagery shows bright blue-white ice faces on steep slopes where the thin soil covering has fallen away. The ice is there, visible, unmistakable. In 2008, the Phoenix lander confirmed it on the ground. Phoenix set down at roughly 68 degrees north latitude in the Martian northern plains. The team commanded the robotic arm to scrape away approximately 2 inches of soil. What appeared underneath was white. The team watched over the following days as it slowly disappeared. Not because it was buried or covered, because it sublimated in the thin Martian air. Water ice, clean and accessible, just below the surface. The extraction process on Mars is close to trivial compared to what the Moon demands. Excavate a few inches to a few feet, scoop the ice, bring it indoors, melt it, filter it. The engineering is well understood. Versions of it have been tested in cold regions on Earth. Or drill a shaft, lower a heating element, and collect the melt through the same hole. This is what engineers call in situ resource utilization, the practice of using local materials instead of importing them from Earth. On the Moon, that concept runs into conditions that break equipment and exceed current technology. On Mars, it is a solved problem waiting for hardware. Water on Mars is not scarce. It is not dangerous to reach. It is not locked behind an energy budget measured in megajoules per kilogram. It is sitting inches below the surface across millions of square miles of terrain. And here is where the story widens. Water on Mars is not just a survival resource, it is a foundation. Every other human need in a closed habitat traces back to it in some form. Drinking requires roughly 3 liters per person per day. Hygiene, food preparation, sanitation all require more. A small hydroponic greenhouse growing food for a crew needs hundreds of liters per day. But water enables something beyond survival. Electrolysis splits water into hydrogen and oxygen. Oxygen feeds the air supply, not as a primary source, but as a redundant one. If the mechanical air recycling system fails, electrolysis of water provides a backup oxygen pathway entirely independent of the machinery that might have broken. Redundancy and life support is not a luxury on Mars. It is the architecture. Water-rich materials also block radiation. Hydrogen atoms are particularly effective at scattering the high-energy particles that make up cosmic rays. This is why polyethylene, a plastic built from long hydrogen-carbon chains, is used in spacecraft radiation shielding. Surrounding a habitat with water layers accomplishes the same thing. Mars provides the raw material for its own radiation shielding. The same substance that sustains the crew also protects them. But the deepest consequence of Mars water is not about survival at all. It is about propulsion. Mars's atmosphere is 95% carbon dioxide. That single fact, combined with accessible water, changes the economics of every mission that ever leaves Mars. The Sabatier reaction takes carbon dioxide and combines it with hydrogen to produce methane and water. Methane is rocket fuel. The water produced in the reaction goes back into the electrolysis loop, which splits it into more hydrogen to feed back into the Sabatier process, and more oxygen to serve as the oxidizer. The reaction is a cycle. Carbon dioxide comes from the air, hydrogen comes from the ice, methane and oxygen come out the other end. Both of them can fill a rocket. This is not a theoretical future technology. SpaceX designed the Raptor engines that power Starship to burn methane and oxygen, specifically because both can be manufactured on Mars. The propellant choice was made with this production cycle in mind. Think about what that means for the economics of getting home. A Mars to Earth return trajectory requires roughly 20 to 30 tons of propellant. At current launch prices, getting 30 tons of anything off Earth costs tens of millions of dollars. Every mission that needs return fuel launched from Earth is carrying dead weight across 6 months of space travel, weight that had to be lifted out of Earth's gravity at enormous expense. Without local propellant production, every Mars mission doubles or triples its launch mass to account for the return trip. The cost math is brutal. Regular missions become nearly impossible. With local propellant production, that calculation flips. Only one-way fuel is needed from Earth. The return fuel is made on Mars from Martian atmosphere and Martian ice, using electricity that comes from solar panels or a reactor already on the surface. The launch cost of the return trip drops to the cost of the equipment that makes the fuel. Not the fuel itself, the equipment. That is not a marginal improvement. It cuts the launch mass of a Mars mission by half or more, and makes regular, affordable missions to Mars feasible in a way they have never been before. But the logic does not stop at Mars. A world with accessible water and a carbon dioxide atmosphere can manufacture propellant from local resources. A ship bound for the asteroid belt or the outer planets that stops at Mars can refuel there. It can leave Earth carrying only enough fuel to reach Mars, take on propellant from Martian production, and continue outward. Conventional chemical rockets, which today would require enormous mass or nuclear propulsion to reach Jupiter or beyond, could make that journey on a more ordinary budget. Mars becomes the refueling node between the inner solar system and everything farther out. All of it rests on one thing: accessible water. The Moon has water locked in the most hostile conditions in the inner solar system, requiring technology and energy budgets that may be beyond what a permanent crewed base can sustain. Mars has water sitting inches below the surface, covering millions of square miles, ready for simple excavation, waiting to be turned into drinking water, oxygen, rocket fuel, and the economic foundation of the next era of exploration. Water was always going to determine whether either world could stand on its own. On Mars, it does not just sustain the people who live there, it sustains every mission that passes through, and the factors that make Mars viable are not finished yet. There is one more factor in this comparison. It is the one that cuts deepest, and the one we understand least. Water determines whether a colony can survive. Temperature determines whether it can function. Radiation and dust determine whether it can endure. But gravity determines something more fundamental than any of those. It determines what kind of people a colony produces. And here, for the first time in this comparison, the honest answer is that we do not know. The numbers sound modest at first. The Moon's gravity is 1/6 of Earth's. A person who weighs 180 pounds on Earth weighs 30 pounds on the Moon. Mars pulls harder. Mars' gravity is 3/8 of Earth's. That same person weighs roughly 67.5 pounds there. The gap between 30 and 67 pounds sounds like a detail. It is not a detail. It may be the most important number in this entire conversation. To understand why, you have to start with what gravity does to the human body when it disappears entirely. We have decades of data on that. The International Space Station has been continuously occupied since November 2000, and the experiments run there have taught us more about human physiology than almost anything else in the history of medicine. In March 2015, American astronaut Scott Kelly launched to the station for what would become a 340-day mission. Russian cosmonaut Mikhail Kornienko launched alongside him. The two of them spent nearly a full year in orbit, while researchers on the ground tracked every measurable change in their bodies. What came back was not reassuring. Bones lose density in microgravity at a rate of 1 to 2% per month. Not 1 to 2% over a career, 1 to 2% every single month. The bones that lose it fastest are the weight-bearing ones, the hips, the spine, the legs, because those are the bones that gravity loads most heavily on Earth. After 6 months in space, hip bone mineral density drops by more than 10%. That is comparable to advanced osteoporosis, but compressed into half a year. The mechanism is straightforward and brutal. Bones remodel constantly. Cells called osteoblasts build new tissue. Cells called osteoclasts break it down. On Earth, gravity loads the skeleton every moment of every day, signaling the osteoblast to keep building. Remove that signal, and the osteoclasts keep working at their normal rate. The osteoblasts slow. The bone disappears. Muscles follow the same logic. Despite 2 hours of daily vigorous exercise required of every ISS crew member, after 6 months in orbit, muscle mass falls by 10 to 15%. The reason is that exercise cannot replicate what gravity does passively. On Earth, your postural muscles fire constantly, even when you are sitting still, simply to hold you upright against gravity's pull. In microgravity, that continuous low-level loading vanishes. No amount of exercise fully substitutes for it. The cardiovascular system weakens. The heart does not need to pump blood upward against gravity, so it does less work, and it shrinks. Blood volume decreases. Astronauts returning from long missions have fainted simply from standing up. The fluid that normally pools in the legs shifts upward toward the head, raising pressure inside the skull. That pressure changes the shape of the eye. Vision degrades. In some astronauts, the changes have not reversed after landing. The spine elongates without compression, producing chronic back pain that could persist for months after return. Immune function drops. Dormant viruses that the body normally suppresses reactivate. Cancer risk rises from radiation exposure and from reduced capacity to repair damaged DNA. Scott Kelly spent nearly a year in space and then spent months in physical therapy recovering on Earth. Some of his bone loss appears to be permanent. Some of his vision changes have not reversed. That is what zero gravity does. The question nobody can answer is what 1/6 gravity does, or 3/8 gravity. Here is where the data runs out completely. We have no measurements, none. The Apollo missions visited the moon 6 times between 1969 and 1972, and the longest any crew spent on the lunar surface was 3 days. 3 days is far too short for the body to show measurable changes in bone density or muscle mass. Those changes take weeks to appear. The Apollo astronauts came home before the biology had time to register the moon's gravity at all, and no human being has ever stood on Mars. Not for a day, not for an hour, not for a second. We know what happens at zero gravity. We know what happens at full Earth gravity. The space between those 2 points is a blank. 1/6 g, 3/8 g, 1/4 g, 1/2 g. Physiologically, that entire range is unexplored territory. We do not know whether the effects scale linearly as gravity decreases, or whether there is a threshold, a specific gravity value below which the body begins to fail the way it fails in 0 g, and above which it maintains well enough for long-term survival. That threshold question is the crux of everything. If the relationship between gravity and bone loss is linear, then 1/6 g produces roughly 5/6 of the damage that 0 g causes, and 3/8 g produces roughly 5/8 of it. Both would be serious. Both would be continuous. Neither would allow healthy, permanent habitation. But the relationship is probably not linear. The body does not respond to most biological signals in a straight line. It is far more likely that there is a critical threshold. Below it, the signaling to bone-building cells collapses, and loss accumulates continuously, the way it does in 0 g. Above it, the signal is strong enough that the skeleton roughly maintains itself, and long-term habitation becomes physiologically viable. Where is that threshold? We do not know. It could be at 1/4 g. It could be at 1/3 g. It could be higher. 1/6 g, the moon might fall below it. 3/8 g, Mars might fall above it. They might fall on opposite sides of the line that separates a livable world from a slowly lethal one. We will not know until people actually live in those gravities for 6 months or more, with bone density measured continuously. That experiment has not been run. But think about what happens if the threshold hypothesis is correct, and the moon falls below it. A permanent lunar base eventually means children. A colony that intends to survive more than one generation has to reproduce. And a fetus developing inside a body subject to 1/6 G experiences different mechanical forces during bone formation than any human embryo has ever experienced before. The skeleton builds itself in response to load. Change the load during development and you change the skeleton. A child born and raised on the moon in 1/6 G might develop bones too low in density to survive Earth gravity. Not just weak, potentially fracture-prone under a gravitational load they were never subjected to during growth. Their heart might not be strong enough to push blood upward against a pull 3 times what they developed in. They might be physically unable to ever leave the moon. Not by choice, not because of distance or cost or time, by biology. Their own body, shaped by the only world they have ever known, unable to withstand the world their species came from. A child born on Mars in 3/8 G might develop closer to normally. The skeleton might receive enough gravitational loading during growth to build adequate density. A Mars-born child might be able to visit Earth after months of preparation, physical conditioning, possibly medical intervention. Possible. Not easy, but possible. For a lunar-born child, there might be no such option at all. That gap matters in ways that go beyond the physical. What if a lunar-born teenager needs a medical procedure available only on Earth? What if they simply want to see an ocean, or stand in rain, or walk through a forest? What if the only world that could treat a rare condition is the one world their body cannot tolerate? The ethical weight here is not abstract. Colonies established in the next 20 to 30 years mean children born in the 2050s reaching adulthood in the 2070s. Not centuries from now. Within the lifetimes of people who are alive today, we will find out whether children born off Earth can come home. This is not the same kind of comparison as radiation shielding or water extraction. Those are engineering problems with known physics, where Mars simply scores better on the measured variables. This is a question about whether gravity might divide a population from the rest of humanity, not through politics or distance or culture, but through physiology. Not a social divide. A biological one. The first speciation event in human history driven not by genetic drift, but by the pull of a world. Mars at 3/8 G is the safer bet. It is not a proven safe bet, but it is the one more likely to fall on the survivable side of a threshold we cannot yet locate. Gravity was always going to matter. The question is whether it matters in a way we can engineer around, or in a way that shapes the bodies of everyone born there for the rest of human history. And we are still waiting for data that will only come from going. Set that profound question aside for a moment. The gravity question sits at the edge of what we can measure. 2 more factors in this comparison sit on firmer ground, and together they form a picture that is almost the opposite of what common sense would predict. The moon is geologically dead. Not dormant in the way a volcano might sleep between eruptions. Dead in the way that matters to anyone trying to build there. The last volcanic activity on the moon ended over 1 billion years ago. The core has cooled and solidified. There are no tectonic plates shifting, no volcanic gases seeping upward, no internal heat that colonists could tap. The moon has been geologically quiet for longer than complex life has existed on Earth. That stillness has consequences that run deeper than atmosphere. When a planet is geologically active, heat and water interact with rock over millions of years. Hot fluids move through fractured stone, dissolving minerals, carrying them along, and depositing them in concentrated seams where they cool. This is how ore deposits form. Not a uniform dusting of metals spread evenly through the ground, but pockets, veins, and concentrations where geology has done the refining work in advance. On Earth, the ore bodies we mine are the legacy of ancient geological violence. Hydrothermal systems, volcanic intrusions, tectonic collisions. The moon has none of that legacy. Minerals on the moon are distributed evenly through the regolith, locked in ancient undifferentiated rock. To extract iron from the lunar surface, a colony would need to process enormous volumes of raw material for a small percentage yield. About 2% iron by weight in a typical lunar regolith sample. That means moving and heating 50 kilograms of dust and rock to recover 1 kilogram of iron. Scale that to the needs of a growing colony, and the numbers become staggering. Mars is different. Geologically, Mars is young. The most recent Martian volcanism may have continued until just a few million years ago. On planetary timescales, that is recent enough to matter. Some researchers suspect certain volcanic regions on Mars might still be active. The evidence is indirect and contested. Traces of methane detected in the Martian atmosphere, which could come from geological outgassing or from biological sources. Thermal anomalies detected by orbital sensors. Lava flows with very little cratering, suggesting they formed after the period of heavy bombardment that pocked the rest of the surface. None of this is conclusive, but the pattern points toward a world that has not finished changing. And here is where the geology becomes directly relevant to survival. The Curiosity rover, exploring Gale Crater, found clear evidence of an ancient hydrothermal system. Hot water once circulated through the rock there, dissolved minerals, and redeposited them in concentrated form. This is the same process that creates mineral ore on Earth. Chemical differentiation. The geology doing the refining that humans would otherwise have to power themselves. Mars has a history of exactly this process. The Moon does not. A still, unchanging Moon sounds safer than a geologically restless Mars. That is the intuitive read. But geological stillness is an economic disadvantage. Not a minor one. A foundational one. A colony that must process 50 kilograms of uniform regolith per kilogram of iron is a colony with a materials problem that never goes away. A colony with access to hydrothermal ore deposits has a workable industrial foundation. That was the geology. But the second factor in this pair carries a more surprising argument, and it starts with the thing most people would consider the Moon's single greatest advantage. The Moon is close. Round-trip communication at the speed of light takes about 2.6 seconds. Near real-time conversation. A problem arises, a call goes to mission control, an answer comes back, a decision gets made. The whole loop completes in under 5 seconds. That feels like a profound operational advantage. And in many circumstances, it is. The picture did not hold. The Moon is tidally locked. The same face always points toward Earth. The far side never sees our planet at all. Radio signals cannot pass through 2,000 miles of solid rock. Any base on the far side of the Moon would need at least 2 relay satellites in lunar orbit to maintain a communication link with Earth. That adds infrastructure, cost, and a new category of single points of failure. If a relay satellite fails, the base is isolated. Near-side polar sites have their own problem. The poles are where the water ice is, but at the poles, Earth sits low on the horizon or below it, depending on the exact location. Terrain can block line of sight. Even a well-chosen polar site on the near side may need relay infrastructure just to maintain reliable contact with Earth. Mars has none of this complexity. Mars rotates once every 24.6 hours, close enough to Earth's rotation that the engineering instincts carry over cleanly. From any point on the Martian surface, Earth rises and sets each day. During the portion of the day when Earth is above the horizon, direct communication is possible. No relay constellation required. No orbital infrastructure needed to reach your home planet. The communication delay runs between 3 and 22 minutes each way, depending on where Mars and Earth are in their orbits. That delay matters, but the geometry is simple and robust. Now consider what happens when something goes wrong. A lunar mission can launch any month. The Moon is always nearby, always accessible. If a crisis develops, an abort trajectory back to Earth takes about 3 days. Mission control is watching in near real time. Rescue is possible. Return is fast. The safety net is real and close. A Mars mission operates under entirely different conditions. Launch windows to Mars open once every 26 months. Miss the window and the wait is nearly 2 years. The crossing takes 6 to 9 months. There is no quick abort. Once a crew leaves Earth for Mars, they are committed for the full duration of the outbound journey, the surface stay, and the return. No emergency resupply. No rescue mission that arrives in days. If something goes wrong on the Martian surface, the solution has to come from the people already there. That sounds like a disadvantage. And in the most direct sense, it is. But follow the logic one step further. A lunar base with near real-time contact and a 3-day abort option will always have a certain character. Decisions flow from Earth. Problems get escalated upward. Resupply solves resource shortages. The base learns to depend on that infrastructure because the infrastructure is there. And because the infrastructure is there, the base never has to become self-sufficient. It stays an outpost. Supplied. Directed. Dependent. Mars does not offer that option. A Mars colony must solve its own problems, not because the colonists want to, but because no one else is close enough to help in any reasonable time frame. That constraint forces a different design philosophy. Every system needs redundancy built in. Every failure mode needs a local solution. Every critical resource needs to be producible on site. You cannot launch to Mars expecting rescue. You must launch with everything needed to survive without it. And the paradox is this. That impossibility of rescue may make Mars missions safer in the end. Not safer in any absolute sense, but safer in the way that matters for a permanent presence. A base that cannot call for help builds systems that do not need help. A base that can always call for help builds systems that always will. One of those produces a colony. The other produces an outpost that will always need to be sustained from somewhere else. The moon's proximity is real. The communication speed is real. The fast abort is real, but every one of those advantages feeds the same structural outcome. A lunar base will remain dependent on Earth for as long as those advantages exist, which is to say, forever. The geology and the communications point in the same direction. Mars is harder in the ways that force competence. The moon is easier in the ways that prevent independence. And the next question in this comparison goes deeper still, because it concerns not what the environment does to the hardware, but what a permanent presence on another world requires from the people themselves. Independence still has to be paid for. Every colony in history, at every scale, eventually reached the same reckoning. The science and the adventure and the political symbolism were never enough on their own. At some point, a permanent human presence on another world has to produce something that justifies its cost. It has to generate revenue, or create value, or become indispensable to something larger than itself. Tourism helps. Scientific research helps. But neither one alone funds a civilization. A colony that cannot pay for itself becomes a liability. And liabilities eventually get cut. So the question is a simple one. What does each world sell? The moon has an answer that sounds compelling at first. Buried in the lunar regolith, the loose surface material that blankets the entire moon to depths of several feet, there is a substance called helium-3. On Earth, helium-3 is extraordinarily rare. The moon has been collecting it for billions of years, delivered by the solar wind, and embedded in the topmost layer of the regolith. And helium-3 has a potential use that, if realized, would make it enormously valuable. It is a possible fuel for fusion reactors. The reaction it enables is cleaner than conventional fusion approaches, producing far less neutron radiation and leaving far less radioactive waste. If commercial fusion power ever arrives, helium-3 could be one of the premium fuels that runs it. That is the setup. Then the data shifted. Fusion power has been 20 years away for the last 70 years. Every decade, the promise renews. Every decade, practical commercial reactors remain just over the horizon. Enormous progress has been made. Several companies and national programs are closer than they have ever been. But the reactors do not exist yet. Not as commercial electricity generators, not as operating plants. The technology that would make helium-3 worth mining is a technology that has not yet been built. Betting a colony's entire economic model on a resource that has no buyer is a specific kind of risk. It is not a risk about the resource itself. The helium-3 is real. It is in the regolith. It can be extracted. The risk is that the economy on the other end of the transaction may never materialize. And if commercial fusion never arrives, the lunar economic case does not weaken. It collapses entirely. There is no fallback. The extraction problem makes this worse. To recover meaningful quantities of helium-3, you have to process millions of tons of regolith. The gas is dispersed at very low concentrations throughout the surface layer. You are not mining a vein or tapping a deposit. You are scooping and heating an enormous volume of loose material to drive the gas out, then collecting it. That requires machinery. Machinery requires energy. Energy in the early years of any lunar base has to come from somewhere, and that somewhere is Earth until local infrastructure is sufficient to be self-sustaining. You are building a large industrial operation on the surface of the moon, powered largely by supplies from another planet in order to extract a fuel for reactors that do not yet exist, to ship back to a market that has not yet formed. Not a marginal risk, a foundational one. Mars's economic picture looks different from the start because it is not built on a single bet. Most of what Mars offers economically is not about shipping things back to Earth at all. It is about supporting the expansion of human activity outward into the solar system. Think about what a fuel depot at Mars means for the rest of space exploration. Mars sits at the inner edge of the asteroid belt, the region of the solar system with the highest concentration of mineral and metal resources. Any mission heading outward toward the asteroid belt or the outer planets passes through the gravitational neighborhood of Mars, a base on Mars that produces its own propellant. The methane and oxygen that can be made directly from Martian water and the carbon dioxide in the Martian atmosphere becomes a filling station for everything beyond it. Missions that would otherwise need to carry all their fuel from Earth could instead top off at Mars. That changes the economics of the entire outer solar system, not just Mars itself. The lighter launch economics matter too. A crewed mission to Mars that manufactures its return propellant on the surface does not need to carry that propellant from Earth. The launch mass drops by half or more. The mission becomes cheaper every time. Mars is not just a destination in that scenario, it is infrastructure. Mars's gravity adds another layer to this. 3/8 of Earth's gravity is low enough to make launches from the Martian surface relatively inexpensive compared to Earth launches, but high enough to make certain manufacturing processes practical that are essentially impossible in zero gravity. Handling liquids, casting materials, operating machinery that depends on consistent downward force, all of these things work on Mars in ways they simply do not work on a space station or an asteroid. Mars at 3/8 G is a gravitational sweet spot for an industrial outpost. Abundant solar power, underground space for protected manufacturing, local raw materials, and a gravity field that makes practical work practical. That combination is not available anywhere else in the inner solar system. But the wild card in Mars's economic case does not come from any of that. It comes from biology. We do not know whether Mars has life. We do not know whether it ever did. But if microbial life is discovered on Mars, even dormant, even ancient, even in trace form, the scientific value becomes nearly impossible to calculate. Every space agency on Earth would want access. Every major research university, every biotechnology company with an interest in novel biochemistry. The discovery of a second independent origin of life would be the most consequential scientific event in human history, more significant than anything we have yet accomplished. The research infrastructure required to study it, to protect it, to understand it, would constitute an economic justification for a Martian colony that no other factor could match. Not helium-3, not fuel depots, not manufacturing. A single confirmed biology discovery would make Mars humanity's most important site on any world other than Earth, permanently. We do not know if that discovery is coming. It may not be. Mars may be sterile, now and always, but the possibility exists in a way it does not exist on the Moon. Decades of lunar exploration have found no hint of organic chemistry, no suggestion of past biology, no environment where life as we understand it could have taken hold. Mars has ancient lake beds. It has hydrothermal systems in its geological record. It has liquid water in its past, and possibly in its subsurface now. The conditions that allowed life to begin on Earth existed on Mars too, for the first billion years of the solar system. The comparison then is this. The Moon's economic case rests on one technology that does not yet exist. Mars's economic case rests on several near-term roles that do not require any new technology at all, plus the possibility of a discovery that would make the question moot entirely. Not a single speculative bet. A portfolio with a wild card at the center of it. And none of the factors in this comparison have yet touched the question that, in the end, may be the most consequential of all. That question is the question of what all of this actually looks like. Not in theory, not as a comparison of factors, as a sequence of events unfolding across decades inside a single human lifetime. So set aside the analysis for a moment. Watch it happen. The first crewed mission to Mars lands, in the most plausible projections, sometime in the late 2030s or early 2040s. The illustrative date that most planning timelines converge on is around 2042. The exact year depends on funding, political will, and how well the unmanned precursor missions go in the decade before. But the shape of that mission is already fairly clear. The crew is probably 6 to 8 people. They are selected with extraordinary care, not just for technical skills and physical health, but for psychology, for the ability to live in close quarters with the same small group of people for months at a time without fracturing. The journey itself takes 6 to 9 months. Cramped quarters, recycled air, limited privacy, constant low-level stress. By the time the crew sets foot on the surface, they will be the first humans to stand on another planet in over 70 years, since Apollo 17 left the moon in December 1972. The landing site will have been chosen from years of orbital reconnaissance, near the equator for warmer temperatures, near confirmed subsurface ice deposits for water access, flat enough for a safe descent. The leading candidates are places already mapped in fine detail. Jezero Crater, where Perseverance found evidence of an ancient river delta, or Gale Crater, surveyed by Curiosity across more than a decade of driving. Both sites offer the combination the mission requires. The crew stays for 18 months. That is not a choice. It is a constraint of orbital mechanics. Earth and Mars align for return windows only once every 26 months, and the crew arrives just after one window closes. So they have 18 months on the surface before the next one opens. Those 18 months are the most important of the entire colonization program. Not because of the science, though the science will be extraordinary, because of what the crew has to prove. They have to demonstrate that human beings can not only survive on Mars, but work productively, consistently, and without the kind of slow physical and cognitive degradation that would make a second mission unjustifiable. They test life support systems under real Martian conditions. They practice drilling and melting subsurface ice. They grow food in a small enclosed greenhouse, the first plants to grow in Martian soil under controlled conditions. They test whether local regolith can be processed into usable construction materials. They document everything. They survey the terrain around the landing site and identify locations for permanent structures. They run medical drills and engineering drills and emergency protocols until execution becomes a reflex. In 2044, they come home, as heroes, with data, with samples, and with something harder to quantify, proof that it can be done. The second mission launches in 2046. This one is larger, 8 to 12 crew, and it carries a fundamentally different payload. Not just supplies and science equipment, permanent habitat modules, inflatable expanding sections combined with hard shell modules for laboratories and airlocks, solar arrays, and at least one compact nuclear reactor for baseline power, full life support systems, greenhouses, medical facilities, basic manufacturing equipment. Some of the crew from this second mission stay, not for 18 months and a return window, for the full 26-month cycle. They are not visitors. They are the first long-duration Mars residents, the first people in human history to make Mars their home for more than a few months at a time. By 2048, when the second mission's remaining crew finally returns to Earth, the foundations of a permanent Mars presence are operational. The habitat modules have been proven under real conditions. The greenhouses are producing roughly 30 to 40% of the caloric needs of the people living there. Water extraction from subsurface ice is supplying hundreds of liters per day. Power is stable. Basic manufacturing from local soil is producing simple construction materials. A second habitat site nearby has been surveyed and prepared. That is when the pattern broke. From this point forward, the timeline stops looking like an exploration program. It starts looking like something else. The third mission arrives in 2048, carrying more colonists. Some crew from the second mission stay. Some return to Earth to write books, give lectures, and spend the rest of their lives being the people who lived on Mars. The ones who stay are the first people for whom Mars is genuinely home. Not a posting, not an assignment, home. In 2050, a mission brings specialists, agricultural engineers, medical doctors, materials scientists, people whose skills are needed not to explore Mars, but to build its infrastructure. In 2052, more habitat modules arrive, along with industrial equipment. In 2054, something changes in a way no previous mission did. The first families arrive, couples who have committed to raising children on Mars. Not in the abstract, in practice. By 2060, there are between 50 and 100 people on Mars, spread across multiple sites. A main colony at Elysium Planitia, perhaps 30 to 40 residents. A scientific outpost at Jezero Crater, 15 people focused on the ancient geology. A polar research station, 8 or 10 people studying Martian ice and climate. Semi-independent sites, linked by communications and occasional crew exchanges. The manufacturing base by 2060 is producing Martian brick from compressed and heated regolith, structural iron extracted from local soil, and plastics derived from atmospheric carbon dioxide. Not full industrial autonomy, complex electronics, precision medical instruments, and advanced materials still come from Earth. But the basics are local. The greenhouses by this point cover thousands of square feet, running hydroponic and aeroponic systems under full-spectrum LED lighting, producing potatoes, lettuce, tomatoes, beans, and wheat. Calories are almost entirely local. What still comes from Earth is coffee, chocolate, spices, things that matter to morale but not to survival. And here is the test. The actual test of whether what exists on Mars is a colony or an outpost. If Earth stops supplying tomorrow, what happens? By 2060, the answer is this. Mars survives. Uncomfortable, lacking luxuries, short on some things it would rather have, but alive. That threshold, the moment when a human presence on another world does not need Earth to continue existing, is the definition of a true colony. Not a flag, not a footprint, self-sufficiency. The first Mars-born child arrives, in the most plausible scenarios, sometime in the late 2050s. A couple from an early mission decides to have a child. The medical facilities can handle it. The birth happens under 3/8 G, in a habitat built from Martian materials, under a sky the child will always know as red. This child will not go to Earth as a child. Their body will develop entirely in Martian conditions. 3/8 G as baseline. Martian atmospheric pressure as normal. The horizon as the only horizon they have ever seen. They will know Earth the way children on Earth once knew distant continents before they were old enough to travel to them, as a real place, vivid in stories and images, but not theirs. Not yet. Maybe not ever. This is not a transplanted Earth person who happens to live on Mars. This is a Martian, the first of a generation. By 2070, if commercial interests engage, the population of Mars could reach 1,000 or more. Mining operations, research contracts, and possibly a small number of extremely wealthy tourists who want to see the place while it still feels like a frontier. Martian society by this point has begun developing its own character. Not transplanted Earth culture with a thin Martian veneer. Something distinct. Its own slang, its own customs, its own sense of what matters and what does not. The children growing up in 2070 will know Earth only through the stories told by their parents and grandparents. For them, Mars will simply be the world. The endpoint, playing out over a century or two, is probably political independence. Not through conflict, through simple inevitability. A self-sufficient population producing most of what it needs. A local economy with its own logic. Communication delays up to 22 minutes each way, making real-time Earth governance not just impractical, but absurd. The natural result is a Martian government, Martian laws, Martian social contracts, with friendly relations toward Earth in the form of trade and scientific cooperation, but political independence as the baseline condition. None of this is a prediction. The dates are illustrative. The populations are ranges, not forecasts. The path depends on funding cycles and political commitments, and technical outcomes that have not happened yet. But here is what the timeline shows when you lay it out concretely. Mars colonization does not require centuries. It does not require technology that does not exist. The path from first landing to first Mars-born children to a genuinely self-sufficient multi-site colony fits inside a single human lifetime. A person born today could live to see it. The children born on Mars in the 2050s will reach adulthood in the 2070s. Their grandchildren may seek independence before this century is over. The question was never whether the science permitted it. The question was whether humanity would choose to do it. That is a different kind of question, and it does not have a scientific answer. And the moon, over those same decades? That is the fair question to ask. Mars gets a vivid arc from first landing to first families to political independence, all inside a single human lifetime. So what happens on the moon across that same stretch of time? The answer is surprising. Not in the way you might expect. Because of proximity, lunar bases would actually grow faster than Martian ones. 3 days from Earth rather than 6 to 9 months. Regular resupply missions. Constant real-time contact with mission control. Rotating crews cycling in and out on reliable schedules. The moon does not need to develop self-sufficiency the way Mars does, because help is always close. Infrastructure scales quickly, precisely because every problem can be solved from Earth. By 2050, there might be more people on the moon than on Mars. Possibly hundreds, working in shifts, staffing research stations and mining operations and communication relays. On raw population, the moon could win that decade easily. But the reading came back reversed. Not one of those people would be staying permanently. Every single person on the moon in the 2050s would be counting down the days until their rotation ended and they could go home. The standard tour would be 6 months, maybe a year for some specialists. Then back to Earth, by medical necessity, not by choice. The moon ends up looking like Antarctica. Antarctica has been continuously staffed by rotating personnel for decades. Important scientific work gets done there. Strategic interests are served. But no one has ever colonized Antarctica. No one has ever raised children there with the intention of never leaving. The people who go there are extraordinary individuals doing difficult work in a hostile environment, and every one of them knows they're coming back. That is what the moon becomes. A permanent outpost, never a colony. The reason is not psychology. It is not a failure of will or imagination. It is the environment itself. The moon's gravity is 1/6 of Earth's. We already know what microgravity does to the human body over months. Bone loss, muscle atrophy, cardiovascular weakening, vision changes that do not fully reverse. The question of whether 1/6 G is above or below the threshold for long-term human health has no answer yet. But no researcher working seriously on this question is confident that 1/6 G is safe indefinitely. And on the moon, unlike on Mars, you cannot hedge that uncertainty. 1/6 G is what the moon offers. It is not negotiable. Radiation exposure on the moon runs higher than on Mars. We covered why in detail earlier. The combination of those two factors alone, gravity and radiation, puts a hard ceiling on how long any individual should stay. 6 months to a year, then rotation, then back, and then there is the dust. We know lunar dust destroys equipment. We know no mitigation system has achieved zero contamination in testing. We know the problem compounds continuously in a way that cannot be solved by bringing more replacement parts, because the dust never stops, and the parts are always coming from Earth. This is not a solvable engineering challenge with an expensive known solution. It is an unsolved materials problem. After decades of research, we still do not have a proven answer. So the moon's population in the 2050s could genuinely exceed Mars's population. More people, more infrastructure, more budget, more political visibility, and every bit of it temporary. The moon would be the more populated world and the less colonized one at the same time. This is the sharpest version of the comparison, and it takes a moment to sit with. Mars is brutal. The crossing alone is 6 to 9 months in a tin can with no rescue available. The surface is cold, irradiated, and covered in atmosphere too thin and too toxic to breathe. Dust storms can blanket the planet for months. Every system fails eventually, and the nearest replacement part, before local manufacturing comes online, is months away. No quick abort once committed. No fast rescue if something goes wrong. But every single one of those problems has a solution, not a hypothetical solution. A working one, or one in active development with a clear path to deployment. Underground habitats for radiation, in natural lava tubes that already exist. Water from shallow buried ice deposits confirmed by 3 separate spacecraft. Solar power for normal operations, nuclear reactors for dust storms and polar winters. Pressurized greenhouses with LED lighting and hydroponics for food. The Sabatier reaction turning atmospheric carbon dioxide and extracted water into methane and oxygen for propellant. Building materials from regolith. Metals from Martian soil. 3-dimensional printing of spare parts from local materials. Breathable air from electrolysis and carbon dioxide scrubbing. Health maintenance from ISS-tested protocols already running continuously for over 2 decades. None of this is easy. None of it is cheap. But the physics works. The chemistry works. The engineering is hard and expensive, and the deployment path is long. It is not impossible. Now consider the moon's unsolved problems. Lunar dust, no proven mitigation system. Every proposed approach reduces contamination without eliminating it. And on a permanent base, continuous accumulation ensures that even 99% removal is not enough. Equipment degrades faster than it can be replaced. After decades of research, we do not have an answer. Gravity at 1/6 g, possibly below the threshold at which the human skeleton maintains itself. Possibly not, but we do not know. And unlike Mars, we cannot hedge the uncertainty. There is no deeper gravity available on the moon. 1/6 g is the offer, take it or leave it. The 2-week night. Solar power is not practical. The alternative is either enormous battery banks, a mass of hardware that would require many launches to deliver and maintain, or nuclear reactors as the sole power source with no backup. A reactor failure during the lunar night is not a managed inconvenience. It is a life-threatening emergency with a 3-day evacuation window and Earth still available. But it is a single point of failure with no redundancy. The 500-degree thermal cycling, every structural element, every seal, every joint, stresses across that range twice a month, month after month, year after year. We have materials that can handle it for a while. We do not have proven materials for permanent structures across decades of that cycling. Long-term material fatigue at that scale has no demonstrated solution. Water in the permanently shadowed craters. The temperature at the floor of the coldest craters is negative 415 degrees Fahrenheit. We established earlier how extreme that is. Extracting ice from that environment requires a deployable reactor rated to operate in those conditions. That reactor does not exist. Building it is not simply an engineering challenge with a known approach. It requires material science that has not been developed. This is the distinction the distance argument misses entirely. Distance is not the right variable to optimize for. The question is not which world is closer. The question is which world's problems have solutions. Mars is farther. Mars is harsher to reach. Mars will take longer and cost more to establish a first presence on. And yet every obstacle Mars presents has a known or near-term engineering solution. A bet on Mars is a bet on hard problems with real answers. The moon's most serious obstacles may have no solutions at all, not with current technology, and not with near-future technology as best as anyone can project today. Maybe material science eventually answers the dust problem. Maybe someone designs a reliable reactor for negative 415 degree operation. Maybe 1/6 g turns out to be survivable indefinitely, and the threshold lies lower than current models suggest. Any of those developments would change the picture. But by today's understanding, the closer world is not the more survivable one. That is not an argument anyone expected to make when the comparison started. It may be the most important thing this entire comparison has found. And it opens the final question this script has been building toward. If the case for Mars is this strong, why has humanity hesitated? So we can finally say it plainly. The moon is Earth's closest neighbor, visited 6 times. The obvious choice. The world every roadmap for human expansion has pointed to first. And yet, across every category that determines whether humans can actually live somewhere for years, for decades, for generations, Mars came out ahead. Not slightly ahead, decisively ahead. Radiation. Mars wins, with an atmosphere thick enough to cut annual dose to survivable levels, and lava tubes ready to shelter the worst storms. Temperature. Mars wins, with a day-night cycle nearly identical to Earth's, and thermal swings a colony can design for once, rather than fighting twice a month. Dust. Mars wins, with particles rounded by 3 billion years of wind. Particles that settle, particles that brush away. Water. Mars wins, with ice sitting inches below the surface at mid-latitudes. Accessible with heat and a drill rather than with reactors operating in conditions colder than anything in the inner solar system. Gravity. Mars wins, occupying what may be the survivable side of the threshold that the moon almost certainly falls below. Geology. Mars wins, with a hydrothermal history that concentrated resources the moon never formed. Communications and mission structure. Mars wins by forcing the design philosophy that produces a real colony rather than a permanent dependent outpost. Economics. Mars wins, with a portfolio of near-term industries and a biology wildcard the moon cannot match. 8 categories. Mars ahead in 8 of them. The moon ahead in 1. Distance. Distance is the wrong variable. That is the finding this entire comparison has been building toward. So, what does the likely real path look like? We will probably do both. Moon bases will come first. They are achievable sooner. They are politically popular. They sit 3 days away, close enough to build confidence and test technologies in a forgiving environment, close enough that missions can abort if something goes wrong. We will build lunar outposts. We will lose equipment to dust. We will struggle with 2 weeknights and 500-degree thermal cycles. We will rotate crews in and out on 6-month tours, never quite staying long enough to become permanent residents, never quite solving the problems that make permanent residency dangerous. After a decade or 2 of that, after barely sustainable lunar operations that teach hard lessons about what survivable actually means, we will turn seriously to Mars. We will have realized the hard way that farther is not always harder, that some environments are more survivable despite the additional distance. And then we will make the leap. The first humans to make that leap will be remembered as the bravest in history. Think about what their daily life requires. 6 to 9 months in a cramped spacecraft with no quick rescue available, no abort option once committed, nothing but the crew and the ship and the void between worlds. Landing where the air is unbreathable and the soil is chemically toxic. Building homes underground, not for aesthetics, but for survival, because the surface radiation budget does not permit anything else. Growing food under artificial light from seeds in pressurized greenhouses, irrigating with water melted from frozen dirt a few feet below the surface, communicating with Earth across a 22-minute one-way delay, which means no real-time consultation, no mission control watching every move and offering guidance, no safety net of accumulated human expertise available in the moment it is needed. Facing mechanical failures and medical emergencies with the resources on hand, and no reinforcement possible for 26 months, the time until the next launch window opens, and a resupply ship can even depart. But here's where it gets strange. Those conditions sound like a death sentence. They are not, because Mars is survivable. The resources are there. Gravity is 3/8 of Earth's, enough to maintain bone density and cardiovascular function in ways the moon almost certainly cannot. The day is 24 hours and 37 minutes long, close enough to Earth's rhythm that the human body adapts. Radiation is blockable with underground habitats and local water shielding. Water is accessible without reactor-scale infrastructure. Temperature swings are demanding but manageable. Everything the first colonists need exists on Mars. It just needs extraction, processing, and the human determination to make it work. And they will succeed. Not because it is easy, because the environment cooperates with survival in ways the moon's environment simply does not. 175 times more distant. That is the gap. Mars is 175 times farther from Earth than the moon is. And yet, across every factor that determines whether a human being can build a life on another world and stay there, Mars is the more hospitable destination. The moon wins on proximity. Mars wins on everything else. The moon will stay important, close, accessible, a proving ground where technologies can be tested and crews trained. Humanity's doorstep is the right image for it. A doorstep is valuable. A doorstep is used every day. But a doorstep is not a home. Mars is the next room. It is where the future gets built, where the first children are born who will know Earth only as a blue dot in a dark sky. A real place, vivid in the stories their parents tell, but not their planet. Beyond Mars lies the asteroid belt, the outer system, Jupiter's moons, Saturn's rings, and eventually in centuries, if humanity chooses it, other stars. But all of it stages outward from the first permanent colony. Choose the wrong location for that colony, and humanity stalls for decades, trying to make an unworkable place work. Choose correctly, and the door to the solar system opens. Armstrong's footprints are still there, pressed into the airless regolith of the Sea of Tranquility, perfectly preserved, undisturbed by wind or rain, because there is none. They will be there 1,000,000 years from now. They are one of the most remarkable things our species has ever made. But footprints are not colonies. Visits are not settlements. Proximity is not viability. When humanity finally builds a true home beyond Earth, one that can survive without constant resupply, with a community that identifies as something other than transplanted Earthlings waiting to go home, that place will probably be Mars. Not because it is easy, because it is survivable. And in the hard arithmetic of space colonization, survivable beats close every single time. Distance is not destiny. Environment is destiny. That is what this comparison found. That is what the evidence across radiation and temperature and dust and water and gravity and geology and economics pointed to from every direction at once. The obvious choice was not the right one. The counterintuitive long-distance bet is the right one. And somewhere in the late 2030s or early 2040s, the first humans will pack into a ship and prove it.